Hello, hi, this is Siddharth. Welcome to my channel. Today, the main topic I chose is the challenges of the machine learning. In this, we'll try to figure out what are the challenges that usually will be faced while we are doing some machine learning programming, and also we want to design a model and what are the usual use cases or the problems we will get it while we are working on this. Okay, so let's dive straight in. So the first topic I want to pick it about it is about the insufficient quality of the training data. The one of the main tasks these days is like everything, even with the machine learning, the major part of this is about working with a data or a model. Sometimes these two things can go wrong, which we can tell it as bad model and the bad data. And let's start with few examples of it. So the first thing is in this insufficient quality of the training data, let's come up with an example. For example, let's see we have a toddler. When he wants to learn something, for example, an orange, he wants to know what is oranges. As an adult, we will show him a round object of with an orange color. By showing them, he can easily understand that is called as an orange or this is called as an apple or something like that. Based on the colors and shapes, that would be very easy. But machine learning is not so quite easy or quite there yet. Okay, the machine learning algorithms to work properly, you need a tons of data for it. Even for a very simple problem, you need a thousands of examples, and for complex problems, you can estimate it how much data you need it, right? Maybe you may need of millions of examples for it. So the data is not actually enough for to train a model in the machine learning, because usually whoever are using this particular models or training a model, most of the people will face that insufficient amount of the data. When you have the insufficient amount of data or the quality is not so good, then the model won't work as you expect. For this, the continuation out of it is we can also see another topic called unreasonable effectiveness of the data. I've also seen somewhere in paper which is published around like 2001 or something. It clearly states that whenever you have a particular model, right, a small model even, that solved complex problems in the real world, right? The idea that we are going to discuss here is it's something like all the complex problems doesn't need a very large complex models. It may be still be solved by a simple means of model that will be enough for you. And it's not only that, it's not always of building a better or complex model, because as the model grows, you need to spend a lot of time on it. And also for that, you need a lot of development work. So the first thing it is you need to think about the effectiveness of that particular model, whatever you will be using, and the data that whatever you will be training on, is it sufficient? We should always think the amount of time you're spending on it and the result you're getting it, right? The major problem is also is about the effectiveness of the data also plays a major role, right? And for this we have an example chat, this efficiency of these algorithms based on the data. If you see here, the training data set and the efficiency of the algorithm. So there are a couple of models here based on, you see, naive Bayes, perceptron, we know, and memory based, and number of words or the millions of words of the training set is increased, the accuracy is also good. So by this you'll also know that the more the data, the more the sample, the more the examples of the data, you may get the accuracy in the model mostly. And the next one is non-representative training data. In order to generalize this, what is non-representative training data, right? Let's suppose, example, you think about any particular graph, for example, with the two parameters where a country and also their life satisfaction index. For that, the main key element you would need is the salary. So basically, by the common sense, you know that mostly the people or the country, whoever make more money, it will be that people will be more happy. Let's think in an ideal situation. But sometimes there may be an entrance of that particular samples of the data will clearly show a particular salary is more high, but this satisfaction index, the life satisfaction index may be low. So whenever you have that outliers, whenever you have training with that particular outliers, the model may not present that actual result whatever we are expecting. So such kind of data, it is called non-representative data. So just taken on an over level, which is not specifically you can use it for your particular model, or which is actually not usable for your particular model also. That kind of data you can come under as non-representative data. And for this non-representative data, we can also take an example of the sampling bias, right? So for this sampling bias, I'll take an example of the US presidential election, right? Around it's 1930 or 1935 something. So what they did is they have sent a particular poll letter to everybody in the US, right? And it's in a large volume, maybe in millions, and they have got a response, at least more than half of that, saying that one person will win. Okay. But what happened when the actual result came up? The thing was, it has been opposite. So if we think by the common sense, so when they have seen that why it happened, why that whatever the sampling they took it, they didn't get the right result. So here what happened was, the people or the company, whoever they tried to send this particular polling information, they need to have this email address or the address. So for this, they tried to get this particular thing from the telephone directories list of magazine subscribers, right? Which is a club or membership list or something like that. If you see that, they all belong to one group of set of people. You can specify as highly classed people or more rich people, right? These all people are mostly, and wealthier people who are there, they are mostly pro towards the Republican, right? And they thought these people would win. On the second side, there are maybe like 20 to 25% of the people who also answered, but the thing is, they don't care about who wins. So they never put the actual thing saying that I would vote it or not. They just ticked on the option, maybe yes or no. Using this sampling, when they have went through this particular test to find out who wins, actually the model got failed. And for this, it depends, you can call it as this particular thing called sampling bias, because a large group of people who are pro towards one specific result, and you're trying to only train the data on that, but sampling who have a biased nature on that particular end product, right? You will never get a right answer, and you can never train a model on top of this. And even when you build a system, recognize any specific kind of videos or the music, right? If you are training only on one set of item of the music, you will never get a right result, right? You should always train, or you should always use different samples, different videos from different countries, different regions, different culture, and with different parameters. You need to add that. If you are just going by only like one place, just a one small region, that will be considered as a bias. And when you use this bias of the sample of the data in your model, you won't, or you can't predict the right results from it. This is one of the thing, the major part in the non-representative training data. And the other major issue is also, you would know, is the particular poor quality data. So obviously, sometimes whatever the example or the sample of the data, you may get it, right? The major issue out of it is the quality of the data. Why? Because it may consist of lot of noise, lot of outliers, and the first basic thing, how you can resolve this, mostly you need to spend lot of time on this data to cleanse it, and also use the significant or specific part of the data where you can use it, and you would know like we can get a right result out of it. In some instances, even you cleanse it, you may see this outliers. At that point of time also, you can decide by yourself to simply discard it, or you want to fix them manually, and you can use it for the modeling. And in some instances, you may also have the missing of the particular values. Let's, if I want to say a particular column or a feature, you may miss lot of values in it, maybe 5% or 10%. Then maybe two chances. One is you can ignore that particular rows or the particular data, or whatever the missing values you have, you can take an median average out of it, median out of it, and you can fill the values with those. It all depends upon how you want to train the model, right? Whenever you have this poor quality data, that's how you can technically correct it. Mostly, as we know, most of the data scientists, including me, will spend lot of time just cleansing the data, making the data correct, and if we have the missing values, based on what methodology we'll use it to fulfill those values. This is also one of the important part. And there is another particular concept or this particular thing called this irrelevant features, right? What is this irrelevant feature, right? It's something like garbage in and garbage out. Your system will only be capable of learning if the training data contains enough relevant features and not too many irrelevant features, based on the common sense, right? If you want to train your model, the features whatever you are using, it should be relevant. For example, think about there is an ice cream shop, right? What you want to do is based on the customer's date, time, and temperature, or something like with this lot of features, you want to find out when and at what particular time the particular ice cream shop will be busy. But for this features selection, if you take some irrelevant thing, something like who is on the another shop or in this opposite shop or something like that, how many people are living side by this another shop, which is like a different, which is like even you can call it as a car shop. You're validating the customers from there, which is irrelevant for this particular job. For this, the feature selection is also one of the important thing. Always remember in such a way, whatever the features you will select it, will it give you a right prediction by training on this feature? That's always the basic thing. You should always remember this by heart. Selection of the features is the most necessary one, right? And the next one will be feature extraction, right? Combining these existing features to produce a more useful one, right? When you don't have this particular features that will serve your purpose, right, you can combine these multiple features together and you can generate a new feature, right, that will be used for training an algorithm. And this creating a new feature is always will happen by gathering the new data, combining together, and you can extract a new feature and then you'll use it for the model, right? This is what it is for the feature extraction. And this is also this one of the major thing about overfitting the training data, right? Usually this particular overfitting happens when the model is too complex relative to the amount and the noisiness in this particular data, right? And overfitting is, you can call it also a trap when you are fitting the data that is not that too much relevant and you keep on training on it, right? You will train after hours, you'll waste your time, and whatever the result you will get it won't be correct. So at the certain level of the training the data with the minimal or the maximum of the data, right, wherever you use it and you train your model, you will see the graph of the correctness will keep on increasing. But if you go on keep increasing this data which is not fitting into your particular model, it suddenly drops it. So we should be also careful when you are training the data, and you should also think about, is it overfitted? How you can overcome this solution, right? There is a simple three-step solution you can use it here. Is simplify the model by selecting only with a few parameters first, right? And by reducing the number of attributes in the training data, or by constraining the model. That is a one. Next, you can gather the more training data that is more relevant, and that will, when you do this feature selection, that is more relevant for this particular model you want to train it to. Third thing, you can reduce the noise in this training data before you train this model, right? The first basic thing is you can reduce this, right, by fixing the data errors and removing the outliers, and also constraining a model to make it simpler and reduce the risk of this overfitting is also called as a concept of this particular regularization. For example, the linear model which we'll define, think about, we have two parameters, theta and theta 1, right? This gives the learning of an algorithm, which you can say of the 2 degrees of freedom to adapt the model to the training data. It can tweak both the height and slope of the line. If we force this theta, the particular algorithm can only have 1 degree of freedom. So what happens here is when you have that one particular feature, it will be very hard to fit the data properly, right? Also, it could do is the basic thing when you train with only one feature, you can only see that straight line or downward trend or the upward trend where it is taking as a part of the increase or the decrease. The trend may be only in the two phases. As you increase on the more features, then you may change maybe the 2 degrees of freedom having the slope and also the theta to tweak the height, right, and the slope of the line. If you have the 2 degrees of freedom, probably you may need more features, and then you can see the model will become somewhat complex, right? And in that complexity also, you have to find the right balance between fitting the training data perfectly to it, right? That is what is all about the regularization. And the next thing is the underfitting. The name itself here says that it is opposite to the overfitting, right? One of the major thing it occurs is when your model is too simple to learn the underlying structure of the data. For example, think about a linear model, right? Where you want to find out the life satisfaction, right? Based upon the particular salary, right? In that, if you're just trying to search with this only two things on with the limited amount of the data, your predictions are bound to inaccurate, right? Because you need a lot of training examples, and also that whatever the examples you have it should be relative to this particular model or particular output you are estimating to, right? So whenever you don't have the right amount of data, so you can call this as an underfitting. And there are also basically three options to fix this problem, right? How you can fix this? Basically, you can select a particular powerful model with more parameters. For example, whenever you're checking a model with only one or two parameters while you're training in between, in the middle of it, there may be many times you would know that this is not the model I want to use it. At that point of time also, you need to revert back and think about it and find a right model that will be used and where you can impose or you can include with more parameters to give the better output. That's one thing. And also feed better. What is mean by here? You need to feed it with an features that are relatively close to this. Using that features, you will get or you will have a confidence where you can get a right answer. And also you need to also reduce the constraint on the model. For example, you can just reduce this regularization on top of it on this hyperparameter, which will fix this underfitting model, right? And using this all these concepts, okay, you can actually train your model better. And under this, even the scenarios, right, whatever we went through this particular, the quality of the data should be more good, and the effectiveness of the data, whatever you're using it, you need to have an adequate sample of the data. You should not use the irrelevant features, right? And also the overfitting is also one of the major problems which will make your model performance very low. Performance in the sense of the result, right? And also this underfitting of the data, you'll also face the problem if the data of that features, you don't have the enough information on it. When you train on it with only few features, your model won't also perform right way. So for that, you also need to have the better model with the more parameters to train on it. And the other thing also about the testing and validating. The only way you know the model is working properly is to trying out with the new cases, right? Or with a test data set where you can see that what are the result is. One way is that you can put your model in the production and you can monitor it and you can see how it performs. This works well, but by suppose if your model is not working properly, there will be a lot of hiccups and also the users will complain. This is not the best idea. The better option for this is usually you can train the data with a sample offset, and you can take the other part of the data to train it, right? So you can train that particular model. Based on that, you can find out is the error rate on new cases is high or low, and you can also evaluate this model on the test set before it goes to the production, where you will have a chances to improve the performances before it goes to the production. From this also you can understand if the particular training error is low, right? Your model is making few mistakes, but this also, the error ratio, if it is low, that is a good amount of chance you can also move it to the production. And also, if the generalization error is high, it means that particular, the basic thing is your model is overfitting the training data, right? So for that, you need to again train the data, and based on that, whatever the results you get it, you can validate it, and you can tune the parameters, or you can add the more features, and you can reduce the overfitted data, right? And then train it again and do this particular process again by testing and the validating out of it, and then you can go into the prod and deploy it. And the other major one is also we need to talk about is hyperparameter tuning and model selection. Evaluating a model is simple enough, right? Just use a test set, and once you train a particular model, how it is working and what is the performance here. Sometimes you may also test this with multiple models. You will train it and use the test data set and how it is working, right? Now suppose a particular model, right, is better, but you want to apply some regularization to avoid the overfitting. The question is, how do you choose the value of the regularization hyperparameter? One option is to train different models in 100 different ways, but suppose you find the best parameter also, the hyperparameter value also, that produces a model with a lowest generalization error, say just even 5%, right? You can launch this particular model in the production, but unfortunately it does not perform as well as expected and produces 15%, then it will be an issue, right? You think about something and then you see that the error will be around like 5%, generalization error will be around 5% or 10%. But if you see, if you once you put it in the production or something like that, and the error rate, whatever you're expecting, it's more than that, then it's an issue. And also, the problem is that you measured this generalization, right, error multiple times on the test set, and you adapted the model and hyperparameters to produce this particular best model for that particular set. So the major thing also is, while you're training this, you can choose multiple models, right, with a same data set, and you can train it and you can hyper tune it, right? But how many models you'll train it? It is also the question, right? The model selection is also one of the major thing before you started, what and which one will serve your purpose, right? And tuning this particular parameters is also not so simple enough, right? You some for some of the model there are a lot of parameters, and based on those different tuning values also you may get different results. So this is also one of the major challenge in this particular machine learning thing. And also the last thing is about the data mismatch, right? In some cases it is very easy to get a large amount of data for training, but this data probably won't be perfectly representative of the data that will be used in the production. For example, think about, you want to create a mobile app to take pictures of flowers and automatically determine their species. You can easily download billions of pictures of flowers on the web, but they won't be particularly accurate, or which we can use it for our training the data, because there may be, and the image is not good, the quality is not good, and some may be in black and white, and you can not recognize this pixel or something, right? As you picked only the flowers data, the images, but when you're training this model, when you see that the pixels, the color of it, and many things may have more issues where you can't get the better result by training on using this data, and when you want to test on it, you may don't get this particular result. So what you have to do here, out of the whatever the images you have it, right, You need to cleanse it. The same thing, whatever you don't feel that is relative, you can discard that particular data, and you can divide this data into the two parts. One, you can put half of them for the validation and other half of them is to train this data. So what happens, based on the same data set, right? You divided this data set into two pieces where you will train with this lot of web pictures on your model. Once this training set, which you have divided the second half on the model to see that how your model has been trained. And from that result also, you can see that if the validation of particular image, whatever you're using the training data, is getting the right result, or it is not, or it's giving any issues, or it has any poorly performance, you can tune it accordingly on top of it. And whatever the data that you have it, you can see it, the data is particularly right. If not, you can just repeat this process to remove that unnecessary data, and you can train it, and you can test on the training data set. By doing this, what happens is you can regularize this model on the specific data set that is nearly useful, and this whatever the features of these images you will be using it, right, you will have a better output. The data mismatch is also one of the major challenge in the machine learning, right? And there is also one more concept which is called no free lunch theorem, right? Technically it is a theoretical principle in the machine learning and in the optimization side. What it states is, if you see, no single algorithm performs best for the all possible problems, right? Technically it's something like that is, you can't use a hammer for every and each and every problem in the world. You need to use a specific tool or specific algorithm for specific problem to solve it. And about the training the data also in the same way. The core idea is, if particular algorithm performs well on some problems, it doesn't mean that it will perform well on all other problems. And if you even apply this to the supervised training, search, and optimization tasks, it won't be always true for only one model. It will be better or good for all the problems in the world, right? You should always find out what is your problem is. You need to deep dive into it. Then you can search what models that may best fit into it. And once you choose the model, what features you need it to do that. This all things are necessary, right? So these are all the, or I think instead of saying all, these are some of the challenges usually this in this machine learning world we will face it, right? And also please find out yourself what may be the other challenges you are facing it, right? And also try to comment it, because what happens is if someone sees it, they can also get that knowledge. That's all for today. So this is all the challenges what you will see in the machine learning. If you like this session, please don't forget to like and subscribe. It may take only a one button to click on the subscribe, but it will help me and it will actually encourage me a lot to actually post more videos on these concepts. And within few days, I'll come up with a new topic. Until then, bye.